Good morning, students.
Good morning, sir.
Good
Yeah,
morning,
good
sir.
morning. Good morning. So I want to welcome you to this class. See if it is 103 class, if you have matter. So this will be the third lecture, the fourth class for the third lecture. So, and as I've told you before, that many times the Zoom may not be able to accommodate all of us because we are more than 1,000. So I have created a YouTube link and I've sent it to our Telegram group. You can tell your friends that cannot join the Zoom to follow through uh, the YouTube link. Good morning. Yeah, I've sent a good morning the YouTube link to our Telegram group. So that's YouTube. That's YouTube talking. So I have to mute it so that we're not disturbed. So anyone that joined through the YouTube, we still enjoy everything we enjoyed on Zoom. So everything. So in the next 1 or 2 minutes, we start the class. But I want to make some people co-host so that when people are disturbing the class, they can mute the person or do other settings to help the class go smoothly. So let me make Adeyemi Uzen a co-host.
Yes, sir.
Okay. You are now a co-host. Then Ojo Praise, you are now a co-host, Ojo Praise, and Adeyemi. Then I think there's one guy called Additional. I cannot see him. Then let me make Oludari Paul a co-host. Oludari Paul. So three of you are now a co-host. Let me look for one more person. So Abdurrahman Anifowoshi, I'll make you a co-host. So 4 people are enough. So if anybody is disturbing the class, you have the right to mute that person, or probably they are doing something that is not in line with the class. You have the right to stop the person. So let's start the class, and I believe you can hear me clearly.
Yes, sir.
Okay. So let's wait for like 1 minute because people are just joining the class. I can see 130 something, and we are like 1,000. So let's wait a bit. When it is 10:02, I will start the class. So before then, let me share my screen so that you can get ready. The co-host should do their work. Co-host, do your work. Those people just locate them and mute them. So let's start the class. So you're welcome to C-Physics 103 class, General Physics 3. And the title is Behavior of Matter. So you can go back to the YouTube again and don't disturb with request for recording. That's why I sent the YouTube link. Go to the YouTube link and you can listen to it there. You can download it and so I cannot be answering like 1,000 students to do recording. Please listen, then go back to the YouTube. That's why the YouTube link is there on our Telegram group. I can still put it on the LMS page so that you can either you download it or you listen to it on YouTube. So, I think we should start from where we stopped last week. So let me stop this sharing. So let's start from last where we stopped last class, so that we can have a smooth class and understanding of the course. So let me go to where we okay. Cool. This is 103, 103. Yeah. Cool. Yeah, this is the lecture note for last week that we could not finish because of the glitch on this Zoom. So we start from where we stopped last week and continue from here to lecture 3. So this assignment, I gave you this assignment before, and I believe everybody has submitted is your own. Then we pick a fixed point last week. We stop at thermometer calibration. Thermometer calibration. So, one of the co-hosts can talk if I ask a question. Can you hear me?
Yes, sir. We can hear you clearly.
Okay. Thank you. Thank you. So I said thermometer calibration. Generally, calibration is the process of standardizing the measuring instrument so that measuring instrument can measure within the range which you have designed it to measure. But now we have taken it down to thermometer calibration, which is the process of standardizing a temperature monitoring instrument to ensure that thermometer measure within a specific range in which it is designed to operate. And that day, I told us the way to calibrate thermometer is by placing them in a thermal contact with any natural system. And I told you the meaning of natural system, that it could be ice or anything that defines a fixed points. Is what we call natural system here, unlike what you know as natural thing in biology. So where we stop exactly is problems with thermometer calibration. I've explained this thermometer calibration and all that into you, but this point is where we stopped. So there are some problems with thermometer calibration. The first one is extreme accuracy is not achievable. There is no way you can calibrate your thermometer that we have a perfect accuracy. It's not possible. We will soon know the reason why it's not possible. Then another problem is limited range of temperature over which they can be measured. They can be used rather. Yeah, some thermometer can measure very high temperature, while some measure very low temperature. Some may not be able to measure high temperature, while some may not be able to measure low temperature. So let me pick the first problem, that extreme accuracy is not achievable. That is, reading given by alcohol thermometer calibrated at the ice and steam points of water might agree with those given by mercury thermometer only at that point, at that calibration point. probably you have a thermometer, alcohol thermometer used to measure the temperature of an object in one environment. Use a mercury thermometer also to measure the temperature of that object in the same environment. So they will give there will be a little disparity between the two. Why? Because the thermometric property in the two thermometers are not the same. They have a different thermal expansion property. So that's why there will be a little difference. But when the temperature you want to measure is on the fixed point, the temperature we agree with, that is, they might measure the same values, the same value. That's what this one is saying. That, for instance, if one gives a reading of 40 degrees Celsius, the other may give a slightly different value. What is the reason? I've said the reason now. It's because the two liquids have different thermal expansion properties. Yeah, they have a different thermal expansivity. So the discrepancy between thermometers are especially large when the temperature to be measured are far from the calibration points. Yeah, I've told you that if you use I'm using alcohol and mercury now, thermometers, to measure the same temperature. They will give you slightly different values. But when you measure fixed point temperatures, they might give you exactly the same. Two of them might give you exactly the same value. But when the value of temperature I want to measure is far from this fixed point that you know, so the disparity become high. So the disparity becomes high. Then limited range of temperature for which they can measure. That's the second problem that I told you. So the limitation is usually associated with the physical properties of the substance in the thermometer. For example, a mercury thermometer cannot be used below minus 39 degrees. So that's another, that is, there is a limit to which each thermometer can measure. Some can measure high temperature. It may not be able to measure low temperature. Some can measure low temperature. It may not be able to measure a high temperature. That's what I'm telling you here, that mercury thermometer cannot be used to measure temperature that is below minus 39 because the liquid inside it will freeze. It will become solid. That's many of it will freeze. And it will not be able to expand again or contract again. So, which is the freezing point of mercury. So, and also, alcohol thermometer cannot measure above 78 degrees Celsius. Or I think I put it somewhere. Because that's the boiling point of alcohol. When you want to use it to measure temperature above 78 degrees Celsius, the liquid inside, which is alcohol, will boil. I will not be able to see the liquid expanding or contracting again. So that's what I'm saying. Then let's quickly look at the types of, and I believe you understand that as simple as that. They have limited range of temperature over which they can be used. There are different types of thermometers. Some of them are, we have liquid in glass thermometers. This is like SS1 topic. Constant volume gas thermometer. We have electrical thermometers. And under electrical thermometers, there are like 3 of them. We have resistance, we have thermocouple, and the third one. Then let's quickly look at the liquid in glass thermometer. So this name, liquid in glass thermometer, they are telling you that it is liquid that is inside, liquid in glass. So you see all this, they are glass, they are transparent glass. So I don't know if you have seen the thermometer before. If you have not seen the thermometer, the one they use in the hospital is an example of a thermometer. It's a liquid in glass thermometer. And if you look at it, it will be transparent so that they can see what your temperature, the measure is. So the liquid here is this black something that you can see. They call it liquid column. So, and the hand here is what is called a bulb. And it must be a heat conducting medium, something that can conduct heat, so that when they place it in a heat bath, the liquid inside it can rise if the temperature is higher, or can go down if the temperature is lower than the normal temperature the thermometer has been taken out from. I say mercury as a liquid can measure between -35 and 350 degrees. So that's an example of this thing that I was telling you. Then alcohol as a liquid can measure between -112 and 78 degrees. You can see. So alcohol thermometer can measure as low as 112. If you want to use a mercury thermometer to measure this kind of temperature, it cannot do that because the mercury will freeze before it gets to even 40. So I gave you the freezing point of mercury up. So look at the mercury thermometer also. It can measure like a 350 degrees Celsius. If you want to use a alcohol thermometer to measure that, the liquid inside it will boil and it will not be able to measure it. That's why they have a limited range of temperature in which they can be used. Then thermometric properties of this type of thermometer is the length of the liquid, which is either mercury or alcohol, that expand in the gas when temperature increases or contract when the temperature decreases. So this is another one. So this is also the liquid column inside it. When temperature decreases, this black thing you see will be going down, until it gets to that temperature to be measured. And if the temperature increases, it will be going up. It will be going up. So this is constant volume gas thermometer. You might have seen this in one of your elementary what's it called, textbook. This is the bulb of that one to place inside each bath so that it can measure the temperature you want to measure. So the working principle of this, you can go and read about the working principle of this constant volume gas thermometer. So just go and read it. No, read it. I may test you on it. So that you have the full understanding of what we are saying. So it is calibrated using ice and steam pumps of water. Yeah. So that's the natural system I was telling you before. So that if you want to calibrate a thermometer, you place it in any natural system. That is the objects that define the fixed points. They cannot be used. These are the proper. I want to tell you the properties of this. They cannot be used to monitor rapidly changing temperature. They cannot be used to monitor rapidly changing temperature. Yeah. They are usually bulky and cumbersome and require a lot of expertise to operate. Yeah. So this one, before you operate it, you need a lot of expertise before you can operate it. Unlike the simple thermometer that you just place on something and you measure the temperature. So constant volume gas is not as easy as that of the simple thermometer. Then it is used to calibrate electrical thermometer. Yeah, this thermometer that you see is one they use to calibrate electrical thermometers. It can measure a wide range of temperature. Yeah, this one can measure very low temperature and it can measure very high temperature. Though it has its own limitation, which you soon see. With the use of different gases, that if you combine hydrogen, helium, and nitrogen, it can measure this temperature -270 degrees Celsius to 1,500 degrees Celsius. So I will not dwell much on that. It's an elementary thing that you guys, many of you know before you enter the university. So let me quickly explain absolute zero temperature. At temperature of the order of 760 millimeter mercury, different gases give slightly different temperature because none of them obeys gas law perfectly. So at this prior, so different gases give slightly different temperature because they do not obey gas law perfectly. So, but when you begin to reduce the pressure, you begin to bring it down, then the gases will be approaching what we call ideal gas. They will move close to ideal gas. And by that, their temperatures begin to agree together. That is, the temperature begin to close together little by little until you get to a point that the temperature read the same value. So let me read the what we have on the slide. As the pressure is reduced, the gases approach close to ideal gas, and their temperature scales agree well together. Therefore, the thermometer's readings are independent of the gas, that is the substance in it. Are independent of the substance, that is the type of gas used in it. And therefore, it is free of the problem mentioned in the previous slide. So it is free from, they will give a slightly different temperature and the range of temperature over which they can be used. So they will be free from these problems once you have reduced the pressure and the gases are close to what is called a ideal gas. So they'll be free from the previous problems in calibration that we have said before. For all the gases, the pressure is 0 at minus 273.15 degrees Celsius. So when you can reduce the temperature of an object to this value, if that's possible, at that point, the pressure will be 0. And this is the basis for what we call the absolute zero scale, absolute temperature scale. That is, absolute temperature scale is a point at which the pressure of a gas becomes 0. Please listen to that statement. It's a point at which the pressure of a gas becomes 0. And I said minus 273.15 degrees Celsius is the 0 point of this scale. And this is often referred to as absolute 0. So because the pressure is 0 at that point, that's why they call it absolute 0 temperature. And this, what's it called? This figure illustrates what I've explained. This is the first gas, the second one, the third one, the fourth, and other one. Then when you begin to bring down the pressure, look at this, these three gases. You begin to reduce the pressure, reduce the pressure, reduce the pressure. And you begin to reduce the temperature. When you get to this temperature, at that point, the pressure becomes 0. You can see the pressure at 6. At this point, at this temperature, and you will see that the three lines has converged to a point here. And the point is minus 273.15. And this is the basis for what we call the absolute 0 scale. So at this point, the pressure will be 0. Irrespective of any gas used, the pressure will be 0. And that's what they call it absolute 0 temperature. Below this temperature, if you can bring the temperature down below this, the pressure becomes negative. The pressure of the gas will become negative. So take note of that too. So that is that. Then let's continue. Then electrical thermometers, I've told you before, we have thermocouples, we have resistor thermometer, we have thermoelectric. So these are the three types of electrical thermometers. So thermocouple consists of thermoelectric consists of two thermocouples that are series connected with a potentiometer and a constant temperature page. So these electrical thermometers, they are more accurate than other, with the exception of gas thermometer. So gas thermometer is the most accurate thermometer. Take note of that. So we say electrical thermometer are more accurate than any other thermometer, with the exception of gas thermometer. And they are quicker in action and less cumbersome. Unlike constant volume gas thermometer that I told you, that they cannot be used to measure rapidly changing temperature. So the electrical thermometer can be used to measure rapidly changing temperature because they are quick in action. They are quick in action. Once temperature increases slightly, they pick up. Once temperature increases slightly, they pick up. So, and they are less cumbersome. So resistant thermometer, it can measure rapidly changing temperature. I've said that. and it can be used to measure temperature between minus 200 to 1000, as you can see, if the resistant wire is platinum. The resistant wire can also be nickel, or it can be copper. So it can be platinum, nickel, or copper. Then thermometric electric property is the resistance of the metal that changes when the temperature changes. So, and I've told you the meaning of thermometric properties. Many of you know that before, but if you don't know it, thermometric property is that property that changes when the temperature of an object changes. So the thermometric property of resistor thermometer is resistance. When you increase the temperature, resistance changes. So that is that. Then thermocouple. There are different types of thermocouple. They can be used to measure temperature between minus 270 and 2000. Yeah, we can see this that this can measure temperature higher than resistance thermometer, and it can measure temperature lower than resistance thermometer, which is minus 270 degrees Celsius. The wire of thermocouples are either platinum or platinum rhodium. And thermometric property is the EMF, the electrical force that changes when you change the temperature. So I will not waste much of our time here. Then the last one, thermoelectric. It can respond to rapidly changing temperature because it has a very small heat capacity. So it has a very small heat capacity. So thermometric property is also EMF, electromotive force. And its measuring element is the welded junction of two fine wire. I think they have told you in secondary school that you just join two wires together at two ends and you put them in a water bed of different in temperature bed of each bed of different temperatures. So the difference in temperature will make the what's it called, the thermometer to read. It can measure temperature almost at a point, very sensitive. Measuring element is very small. Please, can we mute that person? Then let's quickly solve this example. Let's quickly solve this example. This is an application of what we did last week and this morning. So before we now move down to the third lecture, a constant volume gas thermometer is calibrated in dry ice. And what is dry ice? That's carbon dioxide in the solid state, which has this temperature as the melting point, minus 80 degrees Celsius. And in boiling ethyl alcohol, which has the boiling point as 78 degrees Celsius. So this thermometer now, a constant volume gas thermometer, the natural system they use to calibrate it is dry ice. That means the lower point is now minus 80, while the upper natural system they use has a temperature of 78. So this 78 and minus 80 will be the two fixed points that we need. This is no more 0 and 100 that we know before. This minus 80 and 78. So you put that in mind. The two pressures are 0.9 atm and 1.635 atm. So that means the pressure at minus 80 is 0.9, while the pressure at 78 is 1.635 atm. The question is saying determine the fundamental interval of this scale. I believe everybody should be able to do this. I've told you the meaning of fundamental interval. Fundamental is just the difference between the upper and the lower points. So if I want to find the fundamental interval now, so it will be 78 minus 80. That will give me like 158. That's question A. It's no more than that. Since I've told you the meaning of fundamental interval, difference between the upper and the lower, just subtract the two and you have your value. Okay. And I believe you understand that. Then let's move down to the part B question. What Celsius value of absolute zero does the calibration yield? So I want to use the method that I gave you, that vertical lines method. So we want to find the absolute zero of that temperature. That is, if you have used this one as the upper, you have used alcohol, and you have used a dry ice, which has a lower this point as minus 80, what would be the absolute zero of that thermometer? So I have this as the pressure, what's it called, scale, and I have this as the, what's it called, temperature scale. So first and foremost, I mark my lower point to be minus 8 and my upper point to be 78, as you can see. Then this is 0.9 atm. I just convert it to Pascal or to Newton per meter square. I just multiply it by 10 raised to the power 1.01 times 10 raised to the power 5 Pascal to give you this. Or you may not do that. It's not necessary to do that. You may not do that. But I've done that because I'll still get the same, what's it called? The same result. Okay. The solution to question A is 78 minus 80. That's 158. This is fundamental interval that I asked you to calculate. That's question A. But question B is what I'm explaining now. That I mark the lower point to be minus 80, the upper point to be, what's it called? 78. Then the lower pressure is 0.9. And the upper is 1.635. This is a mistake. It should be 1.635. 1.635. Or if I've used the 165, maybe we'll be using that. But just know what I've done. This is the upper pressure they give you in the question. The question is not say, what will be the absolute value of that calibration? So how do we know that? That means they give you pressure. You know, I've told you that the absolute value is defined based on pressure scale, not on temperature scale. The point at which the pressure of a gas becomes zero is what is called the absolute zero temperature. So I'll just come here and put zero there. So it means they give me the pressure. That's why I can put 0.0 Pascal here. Because they say absolute zero, and I know at absolute zero, the pressure will be zero. So I put it there. They give me the pressure. That's zero. Then I want to find this temperature at zero. And look at my arrangement. You will see that this is 1.65 followed by the lower. Then zero is lower than 0. That's why I know where to put it. It's lower than 0.9. That's why I put it on that. Then that means the temperature that I want to find will be here. So let's now apply our mathematics equation 6 that I give you. That for pressure, it will be the what's it called? The reference, which will be 0. Okay, here I do lower. You can do it anyhow, but you must, whatever you follow on the left ear, you must follow it on the right ear. I think I did that in, I think one of these class last week, yeah. So now I put PL, which is the lower, minus P reference, over P upper minus P reference. This is what I give you exactly in equation 6. That is lower minus reference over upper minus reference. I have to do the same here. But if I do reference minus lower over upper minus lower, I have to do it here. I have to do reference minus lower over upper minus lower. Everything that I follow here, I must follow it here too. So it will give me the same result. Okay, let's put our value now. Then the lower is 0.9. I've told you I converted my own to Pascal. You may not do that. It's not necessary to do that. You can use your 0.9 minus 0, which is the reference, over 1.65 minus 0 is equal to minus 80 is the lower for temperature, minus TAB. TAB is that temperature I want to measure, which is the reference, over upper is 78 they give me. minus the reference. I follow the same thing I follow on the left-hand side so that I can have the same result. Then what I did here, I just cross multiply. This multiplied by this, it will be 0.9 multiplied by 78 multiplied by minus TAB equals 1.65 multiplied by minus 80 minus TAB. So I just cross multiply. And you know, if you remove 0 from this, you still have the same value. Remove 0 from this, you still have the same value. Then cross multiply. Then you now rearrange. You rearrange so that you can combine your TAB. So when I rearrange, I have minus 90,900 TAB plus 16500 TAB equals this. So if you do this well, you have your we have 74100 TAB equals this. Then divide both sides by 74100. You have TAB to be minus 273.82 degrees Celsius. So this is absolute scale of that temperature. And you see that it's not the same as the absolute zero, the standard absolute zero that we know to be minus 273.15, because the upper and the fixed point they use in this temperature is not the 0 and the 100 that we know. It's 78 and minus 80. So the absolute zero should give you a slight value different from the normal absolute zero that we know, as you can see here. So as simple as that. This thing is no more than this. If you listen well, you understand it. Then let's go back to the second question or the third question now. What is the pressure at the freezing point of pure water? Here, what do they give you here? It means they give you the temperature, because you know the freezing point of pure water, that's 0. You just go to that scale, that temperature scale, you put 0. This is it, 0 here. They give me. I want to know the pressure. Is that clear? In the question, they gave you something which you should know, because you have the understanding of the freezing point of pure water, which is 0. You have the understanding of the boiling point of water, which is 100. It means here in these two questions, they give you the temperatures. They give you 0 here, but they don't want to write it directly, since they know that you are, at least you are not in primary school. You know the temperature of freezing point to be 0. You know the temperature of boiling point of pure water to be 100. So I'll just come to my scale and put 0. It's what they give me. Then I want to determine this pressure. I'll now apply what we applied before. I can apply P0 minus the lower is 0.9 over 165 minus 0.9, sorry, equals 0 minus 80 over 78 minus 80. So let's see what I've done there. I say P0 minus PL over PL. I'll still do the same for temperature scale too. So P0 is what I want to find. We can call it P0, P subscript 0, or P0 minus that 0.9 over 165 minus 0.9, that's upper minus lower. You do the same thing here. 0, that's the temperature of this pressure given to you, minus the lower over upper minus lower. So when you do that, this normal mathematics that you can do. 16500 minus 90,900 will give you a value. Then after that, you cross multiply. When you cross multiply, you'll be able to find your P0. So I've done my own, and I got 128419.98 Pascal. But because the question is given in ATM, in atmospheric pressure, I have to convert it by divided by 1.01 times 10 to the power 5 Pascal. So I have this. That's why I said you may not convert your own. Just work with ATM. You will see arrive at this value exactly if you have done the normal thing. So the third, the Roman figure 2 of question C. Say what is the pressure at the boiling point. It means they give you the temperature. Just go to your what's it called? Just go to your temperature and put the 100 there. Put the 100 there. Then you now label this one as P100, the pressure you want to find. You still do the same thing. And don't forget the upper and the lower of this case. This is upper, this is lower. Here, 78 is the upper, minus 8 is the lower. That's what you'll be using as the fixed point. So I can still do P100 minus 0.9 over 165 minus 0.9. And I'll come here, temperature is equal to 100 minus 80 over 78 minus 80. So I will still arrive at this is what I've just said. So subtract this, you have this. You have P100 minus 90, this one, over when you add this one together, you have this. Then cross multiply, you have your P100 to be 1736 ATM. So, and I believe that's very clear. So before I move on, any question here? Just 2 questions. And if you don't have, oh. Okay. In the absence of none.
So I have a question.
Okay. Go on. There's no time. Just ask your question.
Sir, is it because pressure is directly proportional to temperature? That is why you did it like this.
I did not consider any proportionality here. I've told you what to use. I did not consider any proportionality. The question is what I followed. So they give you upper in the question. They give you upper to be 78. Upper temperature. Put 78 here. Then they give me lower to at that point. So which is 0.9. Be my fixed point now, not like 0 and 100 that we know before. Do you get? I've not applied any proportionality thing now. I just follow the method I taught you. They now say what absolute zero with the calibration yield. Since they give you absolute zero, you should know that the pressure there will be, I just taught you absolute zero now. The pressure will be zero. What they are telling you is that, oh, at zero pressure, what would be temperature? Then I put it here. I know the pressure is zero. The pressure zero will be is less than 0.9. That's why I put it under 0.9. So the temperature will be TAB. So I follow the same thing. Is it clear or I should re-explain?
Yeah. So if they do for volume, you can do the same for volume for
anything.
any
I've
other
said that last week. Anything, any thermometric property, you can do this. I've said that last week.
Okay, so
You said?
Is that very powerful or 104?
I cannot hear you. Is that what?
Is that very powerful or 104, sir?
You mean, are you talking about the course or you are asking the question?
Is there is powerful?
Okay. Oh, yeah. I think his network is not good. It's terrace power 4, not 104. All this is raised to power. It's not 104, it's not 105. It's raised to power 4, raised to power 5. Sorry, I have to correct that. And I've told you you might not convert your own.
I have a
You
question.
might not convert. Okay.
Sir, is it compulsory that we convert our pressure to Pascal?
What have I been telling you like 10 times? It's not necessary to convert your own. It's not compulsory to convert your own. Where did you put this thing? I just even said it now. That's not necessary to convert your own. It's not necessary to convert your own. I said it more than 6 times. That don't convert if they didn't ask you to convert. Don't convert. Just use what they give you.
Excuse me, sir.
Okay.
Sorry, sir. This question, this one that you just answered now, sir.
Okay.
You know, they asked for the temperature. No, sorry, they asked. Sir, please can you help me take it back to the questions?
So
Sir, so they asked that
Help me mute that
what is the
person.
pressure at the freezing point of water? The freezing point of pure water is 0 degree, and the boiling point of pure water is also 100 degree. But in the calculation,
Yeah.
you use 8 and minus.
Please, the co-host should mute that person. What are you doing? Look for the person and mute the person.
Can you hear me, sir?
That person is disturbing, seriously. Okay, yeah, go on.
Okay, sir. So in the question, they asked that what is the pressure at the freezing point of pure water?
They want you to calculate the pressure at the freezing point.
Yes, and the boiling
Okay.
point of pure water.
Yes.
Sir, is it not 0 degree and 100 degree? That's I don't know, but in your calculation you used 78 degree and minus 80 degree. That was the one that they gave us for Etiwako. So I'm asking that in case we see this question again, is that how we're supposed to solve it?
They are okay. You are saying I should use 100 and 0, right?
Yes, sir.
No.
Like I don't understand.
You have to understand. I've explained it the way I should, and I will still explain it now. I've told you, forget about the 100 and 0 that you know before. Forget about the 100 as the upper point and the 0 as the freezing point. You know, your freezing point now is minus 80. Is what you'll be using as the freezing point. While your upper point is 78 now. That's what you'll be using. And last week, I told you that at times they might give you value different from 0 and 100, you know. So that's what you follow. Here now, they are now telling you, they are asking you to calculate what of the freezing point of pure water. Calculate it on this, what will be the pressure on this scale. So, and you know the freezing point of pure water now, because, the pure water is 0. They want you to calculate the pressure at that point. That's why they give you, they didn't say, what is the freezing point of this thermometer? They say, okay, what would be the pressure at the freezing point of pure water? That is at 0. They don't want to put at 0. What would be the pressure at 0? This is another way to say this question. What is the pressure at 0 degrees Celsius? You just go to your scale. Where is 0 degree? You mark, they give you 0 degree. They want you to calculate this pressure. Do you understand now? Then in your calculation, what you want to do this is not 100 minus 0 and 100 and P naught. It is this 165, which is the upper for pressure. 78 is still the upper temperature. Do you get? This 100 that I put is for second question, the question under it, the last one. So you have to stick to the upper and the lower they have given you. So when I wanted to do my own, where is it? I think is this. Is it this? No, this or absolute. This it. So they say calculate the what's it called? Pressure at the lower point of pure water. So that means the temperature is 0 there. That's why I go to temperature scale straight. I put it. When they ask me to calculate the absolute 0 temperature, I know the pressure is 0. That's why I quickly go to my scale and put 0 on the pressure. I will now mark the temperature scale and put a TAB or whatever symbol you want to use. So P0 is what I want to calculate minus PL. PL is now 0.9 they gave me in pressure over PU. That's 1.65 minus PL is 0.9. Then 0, that's a freezing point of pure water they give me. That's I'll put 0 here. Minus 80, the lower is still minus 80 as they gave me in the question. over the upper. The upper is 78, not 100, because they didn't give me the upper of that thermometer to be 100. That's why I put 78 minus 80. Is that clear now?
Yes, sir. Thank you very much, sir.
So
Yes, sir.
that's
It is clear, sir.
okay. Let's go to the other lecture.
So I have a question about this lecture, sir.
Okay. Okay, ask your question.
Okay, so I noticed that in the first question you used, for the denominator, you used the upper point of P minus the reference point. And usually what we use is upper point minus lower point. So
Upper point.
why was that one different, sir?
Which one? Which one are you saying?
For the first question about the Celsius value of absolute zero.
Okay, let me share again so that
Okay, while you were solving that one, for the denominators of both fractions there, you use the upper point minus the reference point. That's PU minus PR.
Okay, for the what? For the
denominators.
Okay.
And usually we use like PU minus PL. So I want to know why that one was different.
Oh, okay. The problem of you students is that you don't listen well in class. It is when you see what you don't understand that you now pick. I've told you before that the order, what you combine does not matter. In as much as you follow the same thing on your right hand side too. Do you get? If you combine upper and lower as your denominator on the left hand side, that's what you must combine on the right hand side too.
Okay, sir.
I said that before I started that this combination does not matter in as much as you follow exactly the same thing on your right hand side, you will get the same thing. Okay, if I use a reference minus lower over upper minus lower, I must use reference minus lower over upper minus lower on my right side. If I use a reference minus what's it called, minus lower over upper minus reference, I must just follow the same thing on your right. You will get this. Just try. You can go back to your set today. Just take the different combination and you see. But what you do on the left hand side, you must do it on the right. If you miss it, you will not. That's when you will not get it. Do you understand?
Yes, sir.
So I have a question.
Okay, I can hear you. So let me share my screen so that I can start. Oh yeah, ask your question because I want to start this class.
Is this slide available on the LMS? That means you'll be on a PDF something.
When last did you check your LMS?
Always
check your LMS a day before the class. I put it there yesterday.
Okay, sir. Thank you, sir.
Okay.
Hello, sir. Good morning, sir. I have a question, please, sir. Can I ask?
Okay, ask your question, which will be the last question.
Sir, good morning, sir. My name is Alex. Please, sir, where can we get this textbook for this course?
Have you gone to which what's called bookshop? Have you gone? Go to any bookshop you know, standard one. You will get this what's it called? The text that I give you.
The behavior of
There
matter.
are big what's it called, bookshops in Ibadan. So I think there's one around Jericho or so that when I was an undergraduate that I did not see the textbook around the UI. I needed to go to a very far place to get it.
Okay. On behavior of matter, Abby. Thank you, sir.
let's start the second class. So, and what we are looking into today is thermal expansion of solid. So we have wasted our time in asking questions. So thermal expansion of solid and liquids. Though at times it's not how far, but how well. But I want you to listen well. See, one thing about me is that God give me the grace to explain, but you have to listen. Student has to listen. If you listen, many questions that you ask, I've already said them in the what's it called, my explanation. So when you listen well, you'll be able to get what you wanted to ask. So if the temperature of a solid increases, its dimension, it may be length, area of volume, will also increase. We all know that you increase the temperature of a solid, so usually the length will increase, the breadth also may increase, the volume also may increase. So, but if the temperature reduces, they contract, the dimension also will reduce. So, but for liquid, if the temperature, liquid does not have length. So for liquid, if the temperature of a liquid increases, its volume will also increase. So, but there's an exception to this, which is water. There's an exception to this, which is water. When you increase the temperature of water from like minus something, you are increasing temperature from minus something. When water is at minus temperature, it will be a solid, very hard. Then you begin to increase the temperature, the water will begin to expand. It will be expanding normally like the other liquid. But on getting to zero, when the temperature becomes zero, you are now increasing the temperature again. Water will be contracting. Well, when you get to, okay, I say from temperature of less than 0 to 0, I believe you understand this English, like minus temperature to 0, water expand like any other liquid, as I've said that. Then from 0, you begin to increase the temperature until water gets to 0 degree. Within that temperature, water will be contracting. Instead of expanding, you are increasing the temperature. Instead of water to be expanding, it will be contracting. So, and this is contrary to any other materials. Then, once the temperature gets to 4 degrees Celsius, and you are still increasing the temperature, water begin to expand normally again. Water begin to expand normally again. So, and this phenomenon, this behavior of water is what's called anomalous expansion of water, which they always ask you in your work that explain the anomalous expansion of water. You just tell them, when you increase the temperature of water from like let's say minus 4 to 0, water will expand normally. From 0 to 4, water contracts. Then from 4 upward, water begin to expand normally. This is unusual. So anomalous means unusual expansion of water. So this behavior is called unusual expansion of water. Thermal expansion. Okay, this what I've explained is thermal expansion, which has many applications in many areas of life. So for example, let's look at some application. For example, thermal joints are included in buildings, rail tracks, concrete highways, and bridges to compensate for dimensional changes that occur as temperature increases. Yeah. So when they want to lay, want to construct a bridge and they want to lay their rods, they always give space between this rod and this rod, so that when the temperature increases, especially during the sunny day, where this iron increases and this one also increases, so that they will not touch. That's why they tell you they always leave a gap. That gap is to allow expansion. If they did not leave that gap, this array will increase during the sunny day, and the length of this one also will increase, and they will meet and hook up the bridge or whatever they have used it to construct. So as gap are always left between rays to allow for expansion. So let's look at the explanation under that. Expansion is a consequence of the change in the average separation between the constituent atoms in an object. So, for instance, they taught us in the secondary school that any objects are made up of molecules. And especially for solid, their atoms or their molecules are vibrating around the main position or around the equilibrium position. They cannot move far. They will just be vibrating. Then when you increase the temperature, the vibration will increase. The amplitude of vibration will increase. Then when you increase the temperature more, the amplitude begin to increase more and more. And after a while, you will see that there's an increase in the length of that thing. So we see the thermal expansion has taken place. Okay, and then expansion is the consequence of the change in the average separation between the constituent atom in an object. Consider the figure below. This figure, okay, this is the figure I was explaining. So this is one atom. This is another one. This is another one. Then at the equilibrium, what's it called? Not equilibrium position, I mean. At room temperature, yeah, the atoms will be vibrating about their equilibrium position. They will not be able to go far. They will not be able to go far. They will just be vibrating like this. But when you increase the temperature, the amplitude of vibration increases. The amplitude of vibration increases. Then you increase the temperature more. The amplitude begins to increase more and more. And as a result, after a while, you will see that there's an increase in the length of that object. I say at absolute zero temperature, the atoms in a solid oscillate. You can say vibrate about their equilibrium position or about their main position, with an average spacing between them to be 10 raised to the minus 10. That 1 angstrom. That's the average distance between the atoms of an object. So, but when you increase temperature, the distance between them will increase more than this 10 raised to the minus 10, or they can call it 1 angstrom. 1 angstrom. That is as the temperature increases, the amplitude of the amplitude of the oscillation increases. As a result, the average separation between the atoms increases. Consequently, the object expands. That's what happens if you increase the temperature. You see that one object has the length of an object has increased. It means the separation between the atoms has increased. As a result, you will see the increase in the length. Okay, so note, I will stop at this page because there's no more time. It is 10:01. Is it 10 or 11:01 rather? The ratio of the change in the length to the original length to the degree rise in temperature is called the coefficient of linear expansion, which we call linear expansivity, as they taught us in secondary school. So, and they will be saying change in the length per unit length per degree rise in temperature. So it's still the same thing here. So the ratio of the change in the length to the original length to the degree rise in temperature is called the coefficient of linear expansion. And it's denoted by alpha. It's generally denoted by alpha, except it is otherwise stated. If it's not otherwise stated, alpha is always used to represent a coefficient of linear expansion. If thermal expansion is sufficiently small, that is, if the heat you supply is not too great to break the bond between the two atoms or between the atoms, then this proportionality takes place. That is, change in the length over original length is always proportional to the change in temperature. So take note, but the thermal expansion must be sufficiently small, because if it's not small, you will break the bond between the atoms. So where delta T, delta L, and Li are the change in temperature, delta T is change in temperature, delta L is change in the length, and Li is the original length of that object. Hence, I have delta L over Li equals alpha delta T. Alpha is the coefficient of proportionality, which is called the coefficient of linear expansion in this case, so that alpha delta L will be this. From here, I just cross multiply. I have delta L is equal to Li alpha delta T. So which I can write exactly like this. So, and you know that delta L is difference in the length. Final length minus original length equal to alpha Li times change in temperature. Final temperature minus original, minus initial length. Then from where alpha will be this, and this is where the definition comes in. Change in length divided by original length times change in temperature, and this where they bring the definition from, as I've given you here. That's the ratio. Ratio means division. The ratio of the change in length, that's delta L, change in the length to the original length to degree rise in temperature. So this gives us the formula to find the coefficient of linear expansion. So let's stop here. Next week we do the other two. I give you an assignment. I don't think there's an assignment for you today. So we'll meet next class by God's grace. So any question before I leave the class? You can ask your question. You can ask from here or from the previous slide. You can ask your question based on this slide or from the first lecture that we have. We had rather.
Good, sir.
Yeah, good.
So I plan to ask if I had a test next week.
I cannot hear, please. That person is.
Okay, so I want to ask if I'm writing test next week.
Next week, if we have our test, it will not be the day of our lecture. We choose another day different from the day of our lecture.
Okay, sir.
So let's call it a day.
Morning,
There's
sir.
no question. Yeah, good morning.
Yes, sir. This, sir, where can we get all the slides?
The slide is on your LMS.
Okay, sir. Thank you, sir.
Yes, sir.
Good day.
Yes, sir. I want to ask about those atoms that you said they vibrate about their mean position. Why don't they
Yes.
vibrate mean position? Why is it that they have to vibrate around the equilibrium position?
For solid.
Yes, sir.
Okay, you are saying why are they what?
And why are those atoms vibrating around their equilibrium position rather than in that equilibrium position itself? Hello, sir.
Rather than in that equilibrium position.
And rather than vibrating in that equilibrium position, they are vibrating around that equilibrium position.
It's not around, it's not that they are turning around though. What they are saying is that the distance that's separating them, they cannot move higher than 10 raised to minus 10. It's not that they are rotating or they are moving around. Because
Okay.
there's fund binding them together. You did a molecular force now of attraction, right?
Yes, sir.
Yes.
Yes, sir.
So it's that force that did not allow them to go further than 10 raised to minus 10 degree. But when you increase the temperature, it means you have supplied energy to them. Do you get? It's like you two, you have not eaten anything since like 3 days ago, and they want you to to climb a mountain. It may be difficult for you to, but when they give you food and you eat like a bar, you'll be able to climb the mountain very well. When you supply energy, so they'll be able to vibrate further than that 10 raised to a minus 10 meter. Is that clear?
Yes, sir. Thank you, sir.
They are not moving around. They are just, it's like they want to go further, but the force is pulling them back. So not further than 10 raised to a minus 10. Okay, any other question? Okay.
Sir,
I'm listening.
sir, please can you explain the third bullet point? If the thermal dimension is sufficiently small relative to the initial dimensions of the object.
Okay. You know, we said if you supply, okay, we said all objects are made up of atoms, right? Who's that person? Can you hear me?
Yes, sir. Yes, sir.
Okay. I say all objects are made up of atoms, and in solid, those atoms are oscillating about their main position. But when you supply it, it means you have supplied energy to them. They gain more energy to vibrate with a higher amplitude. It means the distance between them begin to do what? Begin to increase. Are you getting it? When you supply it enough heat, when you supply great heat, it will get a point that they will be far apart. And if care is not taken, the force binding them to you break that bond between them. So if you break that bond, at that point, change the length over original length will not be proportional to changing the temperature again.
Reduce. We call reduce.
Are you getting it? I'm looking for that,
Yes, sir.
statement. Yeah. So at that point, the heat supply is not sufficiently small. It's not small again. It is great. It has broken the bond between them. So at that point, that mathematics will not hold again. That change in length over original length is proportional to temperature. This thing, this it. This proportionality will not hold because you have broken the bond between them, because you have supplied great heat. I can break the bond. That's the meaning of this statement, that if the thermal expansion is sufficiently small relative to the initial dimension of the object, then this thing hold. Delta L over Li is proportional to, that is, when you supply small temperature, change in length over original length will be very small. When temperature increases, change in length over original length will become higher. Then you supply more temperature, change in length over original will become higher again. But you must not, like in elasticity, they will tell you so that the elastic limit will not be exceeded. It's still like this statement. Do you get? So you must not exceed, the heat you supply must not be up to that heat that can break the bond between the atoms. Is it clear?
Yes, sir. Thank you, sir.
Yeah, that's the meaning of that statement. So I think we can call it a day. So enjoy the rest of your day.
Sir, what
Okay,
is the name of what is the name of the bond that bond the atoms together?
Go and read your chemistry. I've told you that molecular force is so go and refresh your chemistry what's it called? Your chemistry knowledge. Go and refresh it. So that's intermolecular force between the atoms. So any other thing, let's call it a day so that you can join other class. All right. Enjoy the rest of your day. We'll meet next week. Okay.
Good morning, sir.
Good morning, Oladejo.
Please, will you drop the this class lecture on LMS portal as you drop for us on the
Factual lecture 2.
I told you now. That's why I say you people don't listen. I've told somebody that I've already put this note on the LMS yesterday.
Yes, sir.